get to chat with you today. Let me share my screen. Give me one sec. Actually, do I need permission? Oh, no, there is.
Nope, we should be all set.
Perfect. Okay. Does that look okay?
Looks good.
Okay. So hi, everyone. So I'm Dr. Cynthia Phillips. I'm a planetary geologist at NASA Jet Propulsion Laboratory, and I'll be telling you about one of my favorite places in the solar system, which is Jupiter's moon, Europa. So Europa is one of the 4 Galilean satellites of Jupiter. It's this one right here, and it's about the same size as Earth's moon. But what's really cool about Europa is that rather than being covered with craters and rock, having kind of an old battered surface, instead the surface of Europa is covered with ice. And under that ice layer, we think there's a liquid water ocean with more water than all of Earth's oceans combined. And so I'll tell you a little bit about Europa, why we think that ocean is there, why we think that means that Europa is a great place to look for life beyond the Earth, and then about the Europa Clipper mission. So Europa is one of the 4 Galilean satellites of Jupiter. So there's Io, Europa, Ganymede, and Callisto, and they're kind of like a mini solar system. Io, which is the closest one into Jupiter, is the most volcanically active body in the solar system. And by just looking at its surface here, you can see it's covered with, there's lava flows, there's plumes and volcanoes, they're erupting all the time. There's these sulfur deposits, that's what makes it kind of yellow. Sometimes we call it the pizza planet, because it kind of looks like a pizza. And so Io is, it's a ridiculous place. And it's not a good place to look for life. But then you go to the next moon out, Europa, and this is the world. It's an ice ball. It has this ice layer and then this liquid water layer. And then under that, there's a rocky interior and a metallic core. And as you move further out to Ganymede and Callisto, you can see that those surfaces, you start to see more craters. You start to see older surfaces. The density of craters, so the number of craters that you see on the surface, is often used to date how old a planetary surface is. The more craters, the older it is. So the fact that we see no craters at all in Io, we see just a few on Europa, we see more on Ganymede, and then Callisto kind of looks like the moon. It's just covered with craters. That tells us that Io's surface is really young, so something's going on to happen to change the surface to remove those craters. Europa is relatively young, and then Ganymede and Callisto are older. So basically, here's what Europa looks like up close. It's covered with cracks and ridges. There are places where these cracks are, they're about 2 kilometers or so wide. They're maybe a couple 100 meters tall, but they extend for thousands of kilometers along the surface. And up close, you can see there are these big kind of ridges with a crack down the middle, but then in the background, there's all these small kind of cracks and ridges that just go in all directions. Kind of looks like a ball of string in some areas. There's also regions that are covered with what look like icebergs. This is what we call chaotic terrain. And basically here, we're seeing places where the surface, blocks of the surface seem to have broken up. They've rotated, they've translated, they've even tilted in some places. And then they kind of got refrozen into new positions on the surface. So these are really weird kind of terrains. There's a few craters on Europa. This is one of the big ones called Pwyll, and it has bright rays of material that extend out in all directions from it. And that also tells us that it's a young crater because these rays go on top of all of the other surrounding terrains on the surface. And then we have these weird features called lenticulae, which basically means freckles in Latin. And so these are places where it looks like maybe materials kind of from the subsurface has gotten up close to the surface and just disrupted these small kind of speck-looking regions. So basically, here's what we think is going on inside Europa. We think that there's this ice crust at the surface, and then below that crust is this liquid water ocean. And then under that ocean, there's a rock layer and then a metal core. And so this is kind of like the Earth, except on Earth, we don't have all this ice. On Earth, instead, there's an atmosphere and then an ocean. But on Europa, we're 5 times further from the sun than we are here on Earth. And so there's just not enough heat from the sun to support an atmosphere, to keep water liquid at the surface. But in the subsurface, kind of under this ice layer, there is this liquid water. And so when we compare Earth And Europa on Earth, we think of Earth as this giant ocean world, but in fact, Earth is really just a rock. It's a rock with this little layer of water at the surface. If you took all of Earth's ocean and kind of put it into a ball, this is about how much water Earth would have. This is how much water Europa would have. So it's about twice as much water on Europa as on Earth. And on Earth, wherever we find water, we find life. And so one of the kind of the mantras of NASA has been follow the water. We've gone to Mars, we've looked for water there. And we found, there's some old kind of ice caps at the poles that have carbon dioxide ice, and there is some water ice, but there's no liquid water today on Mars. So when we're looking for life on Mars, we're really talking about like old, dead fossil life that could have existed back a couple billion years ago when Mars's surface conditions were warmer and wetter. But on Europa, that life could be there today. That ocean is there today under the surface. So I always like to kind of, make fun of the Mars people a little bit, who are talking about how Mars is the best place to look for life. We get into a little rivalry. And I think that Europa is by far the best place to look for life. So here's why we think that water is there. So basically, as Europa orbits Jupiter, it gets stretched and tugged by Jupiter's gravity. It's basically kept in a resonance with the other Galilean satellites. And that resonance means that the distance between Europa and Jupiter changes over the course of its 3.5-day orbit. So when it's closer to Jupiter, the surface gets stretched out, and then it goes further away and the surface kind of goes down. This is kind of like how the tides from the moon on the Earth cause the oceans to go up and down. But on Europa, it's even stronger. And here's these animations are greatly exaggerated to kind of show how much is being stretched. In reality, it's nowhere near this much, but that's basically what's going on, is that you're stretching and pulling Europa, and that causes frictional heating. It's called tidal heating. And so models have shown us that there's enough heating just from this tidal heating effect to keep a subsurface ocean of water liquid over the age of the solar system, so over 4 billion years. So that's how that water is kept liquid so far from the sun. And so what we think happens is there's this ocean layer, then there's this warm kind of squishy ice layer, and that's touching the ocean, and then there's a colder, stiffer ice layer at the top. There could be plumes of material erupting from Europa. We have some kind of like tantalizing potential evidence. We don't have full confirmation that there's plumes there. So that's one of the things we're going to be looking for. And we think those broken up kind of chaos terrains, those icebergy looking regions, those could be caused from kind of like thermal plumes of warmer material coming up and sort of causing a subsurface melt lens, a place just below the surface where the liquid could melt. And this is what some of those chaos terrains look like in a little more detail. You can see these iceberg kind of regions. And then here's maybe a way they could form. We don't know this for sure. This is kind of a theory. But if you can get kind of a pocket of liquid, not all the way on the surface, because gravity, ice is weird, or water is weird. Solid ice is actually lower density than liquid water. So this ice wants to float on the water. So it's actually hard to get liquid all the way out to the surface to erupt. So instead, we think that the water could make it about this far up, and then maybe the ice sort of floats and moves around on this sort of subsurface lake within the ice shell. So we think that Europa has all the ingredients for life as we know it. It has water. It has more than all of Earth's oceans. It has the right chemical elements for life. These are things like carbon, hydrogen, nitrogen, phosphorus, sulfur, that are kind of the building blocks for life. And we think that those right chemicals are on Europa. We think there's a source of chemical energy. So the surface of Europa gets bombarded by radiation from Jupiter. And that would be bad for any life at the surface, but it's good because it actually creates oxidants and organics at the surface through these chemical reactions. And if some of that material can make its way through the ice layer into the ocean, that could serve as fuel for a biosphere. And so there also could be hydrothermal systems at the bottom of the ocean. One of the key things about Europa's ocean is that that water is in contact with the rock at the bottom of the ocean. And that's similar to what happens at the bottom of Earth's oceans. And these hydrothermal systems are places where seawater can circulate through hot material, hot rock that's just below the surface. And that can also it can provide fuel and energy for a biosphere, as I'll show you in a minute. And then the final component here is stability. We think that Europa has been simmering for 4 billion years. We think that this configuration here is stable, that ocean has been there. And on Earth, life arose very soon after a habitable environment was available. So we think that on Europa, there's a really good chance. And so here's what hydrothermal systems look like at the bottom of Earth's oceans. So this is not a video from Europa. We have not sent a submarine there. But what we're seeing is these are called black smokers. So they're regions at the bottom of Earth's ocean where there's hot material. There's water that's forced into the subsurface, and then it erupts out in these very high temperature sort of like undersea vents. And as you can see, there's abundant life. This is down at the bottom of the ocean. It's far away from any sunlight that makes it down there. And yet there's all sorts of life that's living there. And so we think that systems like this maybe could exist on Europa as well. And so these hydrothermal systems are one of the best kind of analogs maybe for an environment at the bottom of Europa's ocean. So we're good for all of these reasons. We think Europa is a great place to study. And so the Europa Clipper mission is a NASA mission, and its goal is to explore Europa and investigate its habitability. So habitability is a bit of a weaselly, tricky word here. So here, habitability means, are there places on Europa that could support life? So this is not a life detection mission per se. It's not going to see whether those places are inhabited. It's whether they could support life. Are they habitable? And so to do this, Europa Clipper will study Europa's ice shell and ocean. It'll study the composition of the surface and subsurface. It'll look at the geology of Europa, and it'll also study any possibilities for recent or ongoing geologic activity at Europa, such as plumes, and it'll perform reconnaissance for a potential future landed mission. Europa Clipper will not land. It will not actually touch the surface of Europa. It'll study it from space. So here's what the instruments look like on Europa Clipper. There's a whole suite of remote sensing instruments that go all the way from ultraviolet to a visible high resolution camera, an infrared spectrometer, a thermal imager, and then an ice penetrating radar. And then there's a remote sensor, there's an in situ payload as well. There's a mass spectrometer and a dust detector. These will measure the composition of gas particles and dust particles that are thrown off the surface of Europa into space. They'll actually be able to be scooped up by the spacecraft as it flies past Europa, and their composition can be measured on board the spacecraft. And if there is a plume erupting from Europa, it's possible that Europa Clipper could actually fly through that plume and get a much greater amount of sample. But these instruments are made to work even if there's no plumes at all. They can measure just the composition of the few particles that are thrown off the surface of Europa through charged particle or micrometeorite impacts that throw particles into space. They're very sensitive. And then also there's a magnetometer, a plasma instrument, and a gravity and radio science investigation that will tell us about the space environment near Europa, as well as the subsurface of Europa. And here's what the spacecraft looks like. We're currently building it right now at NASA JPL in the clean room. It has huge solar arrays that span basically, with the solar arrays fully extended, the spacecraft from end to end is about as big as a basketball court. So this thing is gigantic, and that's just because out at the distance of Jupiter, you need a lot of room you need a lot of area on your solar panels to generate enough power to run the whole spacecraft. It has a high gain antenna. That's this dish here that was actually just installed in the spacecraft yesterday. So we were watching that and it was really exciting. And it has, these are the radar antennas. There's 2 long high frequency ones, and then there's 4 of these very high frequency antennas as well. And then there's also a magnetometer boom that's here. So one of the reasons why Europa Clipper has the orbit that it does is that Europa orbits Jupiter inside its strong magnetic field. So that means that the radiation environment at Europa, which is right here, is crazy. And so because of that, if we were in orbit around Europa, the mission could only last for like a month before it just gets fried by radiation. So fortunately, the engineers at JPL came up with this really innovative solution. It's this multiple flyby mission. So basically, there will be about 50 flybys. The spacecraft will be in orbit around Jupiter, and then on each flyby, you kind of go in close around Europa. It's kind of like you hold your breath, you take all your high resolution close approach data, and then you zoom back out. You kind of take a deep breath, you play back all your data back to Earth, and then you send up the commands for the next flyby. So the prime mission for Europa Clipper has about 50 of these flybys over about a 3-year period. And so this will allow us to gather a lot of data without having to sit there and be degraded by all the radiation. So these flybys, this just shows the ground tracks of some of these flybys. And you can see you can really cover the whole surface by building up sort of this web of ground tracks. Let me skip that. So we're currently building the Europa Clipper spacecraft, and here's just some pictures of some of the hardware that's being built. This right here is the vault. This is a radiation protected place on the top of the spacecraft where a lot of the science instruments, their delicate electronics go inside of this shielded box. And you'll see it. You can see it in some of the later pictures of the spacecraft. Here's some of the instruments: the mass spectrometer, that's the gas analyzer, the dust detector. Here's what the boom looks like for the magnetometer, as well as some of the plasma instruments. Here's what some of the cameras look like. So the ICE, this is our wide angle camera. Here's what our spectrometer looks like. And all of these instruments, except for the radar, have now been integrated onto the spacecraft in the clean room at JPL. And here's what it looks like with some of these instruments on the spacecraft. So here's the mass spectrometer. It kind of looks like a death ray or something. And here's SUDA, the gas detector. Over here on the left, that's the telescope for the high resolution camera over here. And a lot of the remote sensing instruments are on what's called the nadir deck, which is kind of on the side of the spacecraft. And this right here is the vault, this box. There's a door that's hinged open right now. So this is the top of the door up here. So eventually, once everything is installed inside, that door gets shut. It gets locked closed with all of the sensitive instrumentation inside. So this picture was taken about a month or two ago. So now the whole spacecraft, and I like this because you can really see some of the instruments. Now though, the spacecraft is getting covered with this insulating blanket. You can see a little bit of it here, but the whole thing is going to be wrapped with kind of this silver foil looking stuff that helps insulate it and protect it while it's in space. And here's what some of the solar arrays look like. You can see with this person to scale just how massive these panels are. These are going to be shipped from Airbus in the Netherlands straight to Florida, where the spacecraft will launch from in October of 24. These will get shipped there next spring along with the spacecraft, and they'll get integrated together at the Cape. And the radar antennas will get attached to the solar panels there as well. So you can watch the assembly. So right now, actually, this whole spacecraft, here's the vault right here. Here's the spacecraft. This is the propulsion module. So this vault has now been permanently attached to the top of this propulsion module. And so it's not going to come apart again. So the spacecraft is basically one giant kind of tower right now. And then they just installed the high gain antenna on it yesterday. So there's a live feed from the assembly room that you can watch. If you go to this link right here, bit.ly/ClipperCam, that will take you to a live feed 24/7 where you can see what all the folks in the clean room are doing. And we also have live chats that we run too, where you can ask questions. And so I often just have this up and on my second monitor as I keep an eye on what's going on in the clean room. So here's what the mission profile looks like. So the launch date is next October, so October of 2024. It'll launch from Florida on a Falcon Heavy rocket. Jupiter orbit insertion is in April of 2030. So that's a 6-year trip to the outer solar system. So basically what'll happen is it'll launch. It's going to head out to Mars for a Mars gravity assist. This is one of the first spacecraft to use Mars for an outer solar system trajectory. Then it'll loop around and it'll have an Earth flyby to build up some more momentum before it finally heads out to the outer solar system for that Jupiter orbit insertion. And this kind of game of pinball is typical for missions that are going to the outer solar system to build up enough speed to make it all the way out to Jupiter. And here's just a little animation of what it might look like as we enter orbit around Jupiter. So as we're kind of in this dramatic shot flying under the spacecrafts. That was the big magnetometer boom. We're seeing the solar panels. We're seeing those radar antennas as we head in to Jupiter, and then finally to Europa. So you can see that Huygens antenna, that's that big round dish that's facing us right now. That will be transmitting all our data back to Earth. So we fly past Jupiter there, and then we finally get our first glimpse of Europa. So these pictures that we're going to get from the spacecraft are just going to be amazing. And I've been waiting for 25 years since the Galileo mission ended in the late 1990s to get some new views of Europa. And so I can't wait to see what we see. So if you're excited by this mission as I am, let me tell you about how you can join us. So we have a campaign called Message in a Bottle, which is a way that you can send your name to Europa. So basically, the Europa Clipper mission is inviting you to sign on to a poem. So this poem was written by U.S. Poet Laureate Ada Limon, and the poem is going to be engraved on the spacecraft, as well as the names of people who are signing on to this message. If you go to this website here, go.nasa.gov/message-in-a-bottle, that will take you to the place where you'll be able to sign up for this. And then you get your little custom certificate that you can save or print out as well. You have until December 31st, so tell your friends and tell your family. And here is Ada Limon, the poet laureate, visiting JPL. So she's looking through the window in the clean room to see the spacecraft, as well as meeting with our center director right here, Lori Leshin. And we also had an event in June at the Library of Congress in DC where we really kicked off this whole campaign. Let me play you this video, and this is going to have sound. So hopefully this will come through. This is the poem.
Did you share sound when you first started to share the screen?
Yeah, did that. Can you not hear the sound?
I don't hear any sound.
No, I don't either.
Okay. Is there a way? I don't know how to do this in Zoom. Is there a way to do that? Okay.
You have to stop sharing, and then before you start sharing, make sure to check the thing that says share the sound.
Okay, let me try that
Should
again.
be in the bottom left-hand corner of the
Okay,
share
so I'm
window.
doing share screen.
And
I'm
there's
doing share sound. Okay, thank you. The poem's worth it. Okay, let's try this again. Let me know if you hear, if you don't hear it, or if you hear
In
it.
Praise of Mystery, a poem for Europa.
Can you hear that?
Arching
Yes.
under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
Okay, so that is the poem as read by Ada Limon, the poet laureate. I just think it's fantastic. It gets me every time. So the poem will be engraved onto a plate, which will be placed on the outside of the vault on the spacecraft. And the names of folks who participate will be engraved on these little tiny chips. We'll have a couple of chips that will be also on this plate along with the poem. So you can send your name and it'll be engraved on one of these chips. And here's what the campaign looks like. So you could read the poem, you can listen to it, and then you can send your name, and then you get a custom certificate like this. So I hope that you will join us on our journey to Europa. We're really excited about this mission, and we think that this is it's a really special mission. And we really want to bring the public, as many people as possible along with us. So there's a bunch of resources on our website. ClipperCam is pretty awesome, obviously, but you can also build your own Lego model. There's also a 3D model you can download and print on a 3D printer, and a paper model you can build. There's an augmented reality experience, as well as some cool coloring stuff. And so here's a link and a QR code that'll take you to the location to get a lot of these resources. And I hope that you'll get involved. So visit our website, follow us on social media, and I'm happy to answer any questions you might have. Thanks, everyone.
All right, well, that was very exciting, and we have a lot of questions in the chat. We may not be able to do them all. Ariana, did you want to prioritize?
Yeah, I can scroll back to the very earliest questions, and some of these you may have already gotten through.
Yeah,
So
I like the question about do we have any evidence as to whether the water is drinkable or not? Does it have enough toxins in it?
Yeah, that's a good question. So we know that the water is salty because we can measure its conducting properties from the induced magnetic field that we see. And so we think it's a bit less, it's kind of like Earth's seawater, but a little bit less salty. So, it's probably not toxic, but it wouldn't be very tasty to drink very much of. You can make a margarita out of it, is what I like to joke.
When margarita works well with salt water?
Well, I'm thinking like the ice and the salt. So yeah, don't actually make a margarita out of seawater. Bad idea.
all right. You already answered how long it will take for Clipper to get to Europa, so it's a 6-year mission. Is that right?
Yeah.
Awesome.
And how long does it take for the data to come back?
It's about half an hour, but it depends on where Jupiter and Europa are. I mean, and Earth are their orbits, but yeah, it's about half an hour, 45 minutes is the one-way light travel time.
We had a few questions about how exactly the flyby works, if that uses a ton of fuel, and how the whole gravity insertion orbit works as well. If you could explain a bit more about how we'll get into Jupiter's orbit.
Yeah, so getting into orbit around Jupiter orbit insertion is the thing that we bring most of the fuel on the whole spacecraft for. So basically there's a big tank of propellant, there's a bunch of engines, and for the orbit insertion burn, it's something like, almost an hour, I think, that the thrusters all burn simultaneously, just to slow us down enough that we can go into orbit around Jupiter. Once you're in orbit, you save as much fuel as you can for kind of these maneuvering thrusters, but basically you're using gravity. So once you're in orbit, the trajectory design team at JPL, I mean, they're like wizards at this. And so they develop these orbits where you have all of these flybys of Europa, but you also use the gravity in some cases of Callisto and Ganymede to help kind of tweak your orbit around, so you can see different parts. So yeah, so we are using a little bit of propellant to kind of tweak the orbit and also position the spacecraft during each of these flybys. But you're using gravity as well, and you want to kind of save as much propellant as you can so you can keep going for longer.
Oh,
Jerry, we're using the raise hand feature if we want to chat out loud, because there's a lot of folks in this meeting, all right? Or the chat. Sid asked a question in the Q&A feature, which I welcome everyone to use. And he asked, what causes the plumes of water to breach the surface? Why doesn't it just stay below the surface?
Yeah, that's a really good question. It's actually really hard to get plumes of water all the way up because of this buoyancy problem. So on Enceladus, which is this little tiny moon of Saturn, we do see a giant plume of material of mostly water being ejected into space. So we know it's possible on Enceladus. Europa has much higher gravity than Enceladus. And so basically to get a plume to eject on Europa, you'd have to probably pressurize it some way. So if you build up kind of a reservoir of liquid, maybe close to the surface, and you build up enough pressure, then maybe if you kind of open a crack, it could sort of almost explosively vent out into space. But yeah, it is actually a hard problem to get plumes to erupt.
Cool. All right. Does anyone else have a question? You're a very efficient question answerer, Dr. Phillips. I think we've gotten through quite.
Maybe the one more. I don't think there's any intention of getting the clipper back to Earth. I think it just stays out there.
Yeah, at the end of the mission. So one of the good things about a mission that's just a robot rather than one with humans on it is that at the end of the mission, you don't have to bring it home again. So you don't have to worry about life support or how you can get back to Earth. So at the end of the mission, for planetary protection reasons, we're actually planning on crashing Europa Clipper into Ganymede. A lot of missions have crashed into, Jupiter or Saturn at the end of their mission. But in the case of Clipper, we're planning on crashing it into Ganymede intentionally. And that's basically so that the last thing we want to do is to crash into Europa where there could be life and sort of kill off that life in the process of detecting it. And so to protect Europa, when we're almost out of fuel, when the spacecraft is still working enough that we can still guide it, right? It hasn't been completely fried by radiation. Then we're going to send it over to Ganymede and we'll crash into Ganymede. And what's cool about that is that the European Space Agency has built a mission called JUICE that's already on its way out to the Jupiter system. And that mission is actually going to orbit Ganymede. And so depending on the timing of the two missions, it's possible that JUICE could even observe that impact into Ganymede, which would be pretty fun.
Very cool.
Wow, well, that was just fascinating. Yeah, I'm just really excited about this mission, and I'm not even a planetary geologist, so I'm an astrophysicist. I normally do black holes, but there's just something about Europa that's always fascinated me. So I'm really looking forward to it. Thank you so much.
Sure. Yeah, it's going to be a fantastic mission, and we're really excited.
So, all right. Well, one person was concerned that there might be life on Ganymede, that crashing the satellite into Ganymede might interrupt.
Yeah, so NASA has planetary protection categories, and basically, while we do think that there is also an ocean on Ganymede, it's a lot deeper down than Europa, so it's way below the surface. So basically, NASA basically decided that it's okay to crash into Ganymede because even if there is life there, it would be in this ocean that's so far down that there's basically no way kind of over the age of, a billion years that the spacecraft could kind of fall all the way through and make its way into the ocean. So that's why we decided that Ganymede was safe to crash into.
Cool.
Awesome.
All right. Well, I think we're at the end of our time for our talk and questions, so we can do our one last evaluation for the summer.
Yeah,
Great.
let's say thank you to Dr. Phillips for
Thanks,
her
everybody.
time.
Just
Excellent.
give little
Thank you.
hand clapping things.
And thank you for all the great questions. That was really fun.
And we'll be posting the talk on our website with Dr. Phillips' permission. So if you want to rewatch it and maybe dig into your questions a bit more, it's always fun to, rewatch a lecture that was really interesting. You might pick up on some facts you missed the first time.
Excellent. Take care, everyone.
All right. Thanks.
Okay, thank you so much.